Seriously, I don't understand a lot of the astrophysics. I'm not an expert on astrophysics. And so in that, I want to explain that the reason I wanted to give this talk was to illustrate Stephen Hawking. And at one point, I said in church, I think Joys and Concerns, how I'd read his little book. And I was amazed how he was out there. So he wrote this book. He wrote more than one, I think, but there's a brief history in time from Big Bang to black holes. Can we put that picture of him? It's titled Hawking. Can we put that up, share screen? So what I want to say too about him is he was diagnosed kind of early in life with ALS. And I don't understand a lot about ALS, but it just ravaged his body. It just brutalized his body. It just wreaked havoc. And you can see there, you've got his picture there. He's in that wheelchair. However, it didn't harm his brain. And he was able to, sort of travel through the cosmos, using his brain. And of course, he got his PhD and he added, to the body of knowledge, fairly extensively. The biggest thing I think people remember for him is his research on black holes. And of course, most of this astrophysics stuff, mathematics precedes the experiment or the evidence, so to speak. So he was, doing this mathematics on black holes and trying to figure out how they would work. And I have a little bit about that later in the talk. But I want to go back now, having introduced Stephen Hawking and my purpose. And I printed a little book, made a couple little books. There's a real good little summary here. I was going to leave one in church. I like to make these little books. I used to do this at work all the time. You find a good, PDF or something and print it and bind it, I had to put the binding on the wrong side because of the way the margins are too close on this side. But in fact, here's some of his awards. In 1966, there's an Adams Prize. There's all kind of Royalist Astronomical Society gold medal. In 2009, President Obama gave him the Presidential Medal of Freedom. There's a picture of that in here somewhere. And there's a couple other, there's just a whole list of awards that he received. And, the whole time he married, when he was young, he was sort of physically normal. And when he married, it was beginning to affect him, but not so badly, but the disease just progressed through the years. He had 3 children. But the disease, progressed through the years to where he couldn't talk at the end of it. You couldn't understand him at any rate. He could make a sound, but he had a kind of a voice synthesizer or something he would speak through. And you can imagine too, he's doing this, he must have been doing this mathematics largely in his head, because he couldn't hardly write. So now what I want to do now, and what I want to do now is do a little history lesson. Where's my piece of paper? I always end up fumbling with paper. Okay. So now we're going to go back before the windmills, as Wayne was talking about, the windmill power. Before the windmills, go way back to Aristotle. And which is looking like about, it says the Pythagoras talked about a spherical Earth in 500 BC, and it says Aristotle validated it 200 years later, so that'd be 300 BC. He had 5 arguments arguing for a spherical Earth. One was the gradual disappearance of ships over the horizon, the tops of the sails disappearing last, the curved shadow of the Earth on the moon during eclipses. There was a couple others, let's see. And then they said this one really didn't, they didn't really rate this one highly in the reading I was doing, but I thought it was kind of good. He says, matter tends to form into drops or globs, and the Earth, in forming from chaotic matter, did the same. You know, that's kind of amazing, I think, that he concluded that in 300 BC. Now, as is often the case, well, let's see. Then Eratosthenes measured the circumference of the Earth. Let's see, what year? 240 BC. And the way he did it, I've got a picture which is called, I only have, do you see that? Measure the Earth, Measure Earth is the picture. I think this is kind of interesting. Amazingly, too, I don't fully understand this one, but he put 2 sticks in the ground, so to speak. One was, where is that picture? Because I need to read it. In one town and the other one was in Alexandria. And he measured the sun at zenith and the shadow. And he hired a man to calculate the distance. He didn't have Google Maps, you know. So he hired a man to calculate the distance between these 2 cities. They come up with, I think, does it say 800 kilometers or 500 kilometers? Anyway, then he figured that the way the sun was hitting these 2 points in the cities, it was 7 degrees. So he divided in 360 degrees and come up with 1/50th of the circumference of the Earth was exhibited by these 2 cities, and the distance apart, multiply it by 50, and you get the circumference of the Earth. That's 240 BC. As is often the case, readers of the Bible held this knowledge back. Isaiah 11:12 refers to the 4 corners of the Earth. Now, I like to say, too, it wasn't the Bible that did it. It was the readers of the Bible that insisted that the Earth was flat. And, of course, our history is tied in with Christopher Columbus, who was supposedly going to prove the Earth was round, right, in 1642, something like this. Amazing. But that's our history. Moving on. In 1687, Isaac Newton and Robert Hooke came up with the mathematical formulas that describe the role of gravity. In fact, and Newton published a formula that actually is used, the same formula is used to determine velocity required to put an object in orbit around the Earth. 270 years would pass before Sputnik 1 actually orbited the Earth in 1957 and caused a great panic in the United States and started the space race. And Kennedy said, we don't go to the moon because it's easy, we go because it's hard, right? Something like that. But, okay. Now I'll go back again. I jumped ahead in time. It's my lifetime. Imagine that. 1859, Civil War era, Darwin came up with evolution. Now, of course, I mentioned earlier how, you know, the Bible influenced the Western world, you know, a great deal, particularly up until the time of Darwin, I would say. And this idea of evolution really hit the Bible readers hard because it seemed to take God's job away from him. At least maybe he minimized God's job so that, you know, life evolved until the man formed, and like Adam, like on the ceiling of the Sistine Chapel, when God just reaches his finger out like this and Adam's got his finger, you know, and they just kind of touch. So then God just gives Adam a soul at that point, perhaps, you know. He really didn't have that much to do anymore, you know. We kind of figured everything out. And also, and then so we still, of course, they still said, well, how did life begin at all? Well, there was, and in high school, I learned about coacervates. So there was a Russian biochemist, Oparin, and British biologist Haldane hypothesized in the 1920s that the first cells in early Earth's oceans could be in essence, coacervate droplets. And so the concept is the Earth at the, millions of years ago was a primordial soup, a dilute mixture of organic molecules that could have build up of the result of reactions between inorganic building blocks such as ammonia, carbon dioxide, and water in the presence of UV light as an energy source. And as I recall, there was scientists that sort of conducted an experiment, produced a type of life from these coacervates. And, you know, if you think about if you think about what is life, if you think about a virus, there doesn't seem to be much about life in a virus. There, we can't relate to a virus. I don't mean to say that the symptoms of it. I mean to say when you look at it as a life form, it doesn't really seem very much like a living thing, but it certainly has the urge to reproduce, which is a trait of living things. So along with this idea, all these two ideas, life starting on its own, so to speak, from the primordial soup, from the sort of environment that existed, and evolving. And then in addition to that, it was kind of thought the universe existed forever. And it wasn't well understood, but it's like that was sort of the general thought. Rocks seem sort of infinite, not infinite, what less forever, anyway. So, like, really didn't need God anymore, at least not in a serious way. Maybe he helps things along a little bit here and there. It's not for sure. In a certain year, which I didn't fill in, which I think it was in the early 50s or 40s even, Alexander Friedman and Edwin Hubble showed that the universe is expanding. This was done in the way I'm going to try and do like when you're on a highway like Lancaster Road heading out of Richmond, and a Kentucky pickup truck that has a sort of a challenged muffler is approaching you, and then it goes by you. It's like, so it sounds different when it's approaching you, and it's as compared to when it's going away from you. And it has to do with the way the sound waves are compressed or sort of widened, depending on whether it's coming or going. So light, although the speed of light is locked in, which I'll get to later, the waves can change based on whether something is moving toward you or away from you. So this was what they did. They kind of thought when they started looking at stars and planets and stuff like this, they kind of thought they'd be going this way and this way, kind of a random motion. But they discovered that everything was moving away from us. The universe is expanding. The scientists at the time was like, oh, I could have had a V8, you know, why didn't I think of that? Of course, the universe has to be expanding. If it didn't, gravity would cause it to collapse on itself. So this brought about, well, if the universe is expanding, it sort of comes to sort of think, well, I guess at one time it was in one place. So this brought about the Big Bang Theory. In simple terms, the idea began from a pinprick of a massive amount of energy, which essentially exploded into the universe to be the universe and the Milky Way and the solar system. Whoops, God has a job again. Oh boy, now we need somebody to provide an insane amount of energy in a pinprick of space, which can explode into the universe. In the early 1950s, Pope Pius XII not only declared that the Big Bang and the Catholic concept of creation were compatible, he embraced Lemaitre's idea of science, which I don't have the information on that. But I think what he's saying is he embraced all the calculations, the whole thing. This is how God did it. And I think that's hilarious. That just cracks me up. And there's certain efforts to figure out a way that it could have sort of happened on its own, but I don't think it hasn't gone well, really. I was going to read real quick. I think okay, so here's what let's see. As described by what is called inflation theory, in trillions of the first second, the universe underwent a sudden inflationary burst during which it expanded to perhaps 10 to the 50th time its original size. Let's see. After 1 second, the temperature had dropped to 10 billion Kelvin, the temperature at the heart of an H-bomb explosion. Particles such as photons, electrons, and neutrinos would have reacted with each other and with their mirror image antiparticles, creating and destroying matter and annihilating each other in a subatomic maelstrom. After about 3 minutes, the temperature would have dropped to 1 billion Kelvin, which occurs today inside the hottest stars. At this heat, nuclear reactions are possible. Protons and neutrons paired off to produce the nuclei of deuterium atoms. In their turn, about 25% of these nuclei each absorbed another proton and another neutron to produce helium nuclei. And then the other big component was hydrogen. The very early universe consisted of 75% hydrogen, 25% helium. But I think it's, so that's all I'm going to read about that. But they do all kind of calculations and stuff to come up with this stuff. It's just, the point is, it's like, he's out there. And Hawking's is, he's standing on the shoulders of all these men of knowledge, as we say, and going farther. 1916, so I jump back again. I want to talk about Einstein briefly. So there was, they were doing scientists were attempting to do some calculations, and they were assuming that this time didn't vary. Time was locked in, never changed anywhere, anyway, for any reason. But the speed of light could change. So they were trying to set up their calculations, and it wasn't working out. So Einstein addressed these two another problem is, well, I think I got to do it this way. So Einstein said the reason you're having a problem is because your assumptions are incorrect. Time varies, the speed of light does not vary. And this caused the calculations to work. Now we get into something I really don't understand. But one thing I really like, can we do the picture of space-time? Bring up space-time. I really like saying space-time. I like hearing space-time. It just has such a nice ring to it. I just feel like it's that's it. It's space-time. So somehow, which I don't understand, time changes. The passage of time is different depending on gravity. So they say, and they'll get into all kinds of crazy stuff, like if you're on the first floor, if you're in this first floor, time is normal, so to speak. Time passes normally if you're on the first floor, but on the second floor, it's going slower for the person on the second floor. I don't understand it. But one thing on David I know it's mentioned to me before is, so the farther away you are from the center of the earth, the slower time is going to be for you. And so when they do the GPS satellites, where we do our navigation now, exact precise time is critical. It's got to be absolutely positively exact when you put everything together and get your navigation. So they have to modify the time, and these satellites are over the earth, farther away from the center. They have to modify the time that these satellites are experiencing because it's different. I don't understand it. And then, so we got space-time. Now, here's the other thing. So the speed of light does not change. It's 386,000 miles per second. And, but gravity, and nothing can go faster than light. Nothing can go faster than the speed of light. One other thing about time, too, they say as you go faster, time slows for you. And, which I don't understand that either. But then you got it's space-time, I guess. So the gravity alters space. So that there's not a force there that happens instantaneously faster than light. It's a modification of the space. So when you've got a rock or weight on the end of a string and you spin it like this, you could spin it and it'll go around. That's basically like a satellite orbiting the Earth. So the string is the force that keeps the rock from going in a straight line, which is what it wants to do. Well, gravity isn't a force in that way. It's got this space-time curvature. So sort of the easiest or the natural path is to follow that space-time curvature. And we have this little diagram. It's like two-dimensional, but it's a three-dimensional thing. And actually, they say four-dimensional because of time. Which they can't really picture it. They can't really do a picture of it. Speaking of time, I'm getting close to probably letting David David's going to talk about wants to talk about time cones too, and I have a couple. You want me to do it? Because I don't understand these time cones either. But I have a picture of the time cone, which is called time cone 2. And I really shouldn't even hardly say this because I don't understand. But I've got a little thing I can read here. So it says space-time diagrams and light cones are useful tools used by physicists to examine the effects of relativity. The outer edge of the cone represents the speed of light. Thus, no event within the cone can be causally linked to an event outside the cone, as it would require a signal traveling faster than light. So if you understand that, explain that to me afterwards, please. I think, do you want to go, David? Are you ready?
I was just going to wrap it up, and a lot of what I was going to say was already been said.
I have some other stuff here. What do I have? Gravitational time dilation. One thing I did want to say too a little bit about, so Stephen Hawking talked about black holes. Let's talk about that a little bit.
Hawking radiation?
Yeah, Hawking radiation. So by 1973, classical black hole theory had reached a degree of maturity. Black holes, however, contain space-time singularities. So one of the things too that I think Stephen Hawking is known for is this concept of singularity, which to me, it sounds like another way of saying miracle, but it's a singularity is a region where general relativity breaks down, raising fundamental issues about the nature of space and time. And I guess I shouldn't say that about the miracles. So it's a place where I guess you would say really we don't understand the physics in a singularity is probably a better way to say it. Another thing I haven't talked about is quantum theory, which is, and I was going to mention too, like Newton. So everything we do, we use Newtonian physics for everything we do. We drive our cars and build our houses, and it's all Newtonian. There's no need to get into quantum physics. But when you look at the atom, look at nuclear, look at the smaller particles, you have to get into quantum physics to understand it. And there's like gravity, like, you know, there's electrons spinning around the nucleus, but it's not gravity. There's a strong force and a weak force, and I don't know, they're still trying to kind of figure it all out. There was another thing about quantum theory that, you know how they're trying to build quantum computers. And as I understand it, which of course, as I've mentioned before, I don't understand any of this stuff. There's a particle, when a particle exists in one place, there's a sort of an anti-particle that exists in another place, a sort of a twin. And somehow they're trying to use this fact to do this quantum computing, which is going to be a total and complete breakthrough when they get it figured out. A little bit similar to the fusion, which does not produce the radiation. It's a form of nuclear energy, but it doesn't produce radiation. That's another thing they're trying to figure out, and it hasn't happened yet. But Stephen Hawking, he did a lot of studies on black holes and singularities. And the black hole is a kind of a singularity because, it has this incredible gravitational, well, it has incredible mass in a small space, I guess. Let's see, what else have I got in here? Entropy proportional to the area of its event horizon. So we don't know what that means. Stephen was highly skeptical because black holes would then have a non-zero temperature. Any object with a temperature emits black body radiation, but black holes were thought to be unable to emit anything because of their incredible, gravitation. So, which would be which would be the way they warp space-time. So Stephen began to study how particles and fields governed by quantum theory would be scattered by a black hole. Earlier studies of superradiance had shown that an incoming wave could be amplified by scattering off a spinning black hole, and had even indicated, as an extension, that a spinning black hole could superradiantly scatter vacuum fluctuations, causing spontaneous particle emission that spins the black hole down. At the Krakow meeting on cosmology, September 1973, Stephen met Zeldovich and Alexander Starbinsky, who pointed out to him that this spontaneous emission stimulated by these discussions, Stephen discovered a few months later, much to everyone's surprise, that all black holes, even those that do not spin, have no spin energy to extract and emit particles at a steady rate. Initially, he thought there might be a mistake in his calculation. So once again, he's doing these calculations, you know, while he's trapped in this wheelchair, in his head primarily. And he's attending these conferences too, all over the world, where they talk about all this stuff, people that really understand it. I just thought of something else. What the heck was it? Oh, I know what it was. So we mentioned the concept, Einstein's big contribution, you know, one of his big contributions was his concept that nothing can travel faster than the speed of light, and light always travels at the same speed. They have an accelerator, a particle accelerator in Europe, and it goes underneath a couple of cities. It's so enormous. I'm going to guesstimate it's 20 kilometers in length or something, or diameter maybe. It's underground, and it's, as I say, it's enormous. And they accelerate protons. They have this massive machine to accelerate this incredibly tiny particle, not even an atom, just a proton. And I was reading where they have a spin up. So they started out in one place and spin it up to a speed. And then I think they spin it up to another, and then they put it in the big one. And they get it very close to the speed of light. So I was kind of wondering, does the mass of the proton increase greatly? Because that was the E equals MC squared. You know, that's the concept. The reason you can't travel faster than light is your mass would increase so much, too much, to an infinite amount, I guess. I don't know. And the reason they're doing this, they accelerate the proton like that. They smash it into another proton, and then they look at what's given off. So they're looking at the particles that compose that the proton is composed of, and it becomes like quarks and all that stuff. So now I'm going to let David do his thing for a few minutes. I took up most of the time, but maybe he could sing his song again. It was.
Yeah, I was actually, No, I'm sorry about the song. It's just, you know, at home, the lyrics are fine, but in here, it's so different. But basically, you know, Bill, you know, he spoke on a lot of different issues. And the only thing I wanted to mention was, well, the Holy Grail of modern day physics. They look for a unified field theory. Their goal is to find the four assigned forces of energy: electromagnetic, you know, gravity, the strong nuclear, weak nuclear force, fundamental. Okay, so they want to basically find a unified field theory that combines everything, basically. Question: if the universe is a result of ever more complex functional relationships, which the whole homily was about in my way of thinking, becoming from one holistic reality, such as Big Bang, hydrogen becoming ever more complex through myriads of stars, and which was talked about already. Cannot this be used as a guide in gaining appreciation? The universe reflecting a transcendent reality, a cosmic oneness, which of course we are an intrinsic part of ourselves. We are made of the very elements fused in the stars. Surely the all-embracing unity so manifest throughout existence should be the most evident proof of this oneness of humanity. If this is the case, the seeming differences we experience in our everyday lives, the petty differences so prevalent among the religious and political institutions of people on this little earth, orbiting an average star located in no particular place of importance within an average galaxy containing perhaps 200 billion stars, pales into utter insignificance. From this universal unity, the universe has become manifested with a diversity, power, beauty, and perfection in which one can only marvel.